Okay, good evening. Welcome to Geometry Project 11. This is section 2.2 of Geometry Revisited, the radical axis of two circles. So we're going to learn about something called the radical axis, and we're going to prove the following theorem. The locus of points whose powers with respect to two non-concentric circles are equal. So you take the locus of points with respect to two circles who have equal powers, and that is a line perpendicular to the line connecting the centers of the two circles. So it's just an interesting fact about the power of the circle. If you don't know what a power of a circle is, that was Geometry Project 10. So that's section 2.1 of Geometry Revisited. So let's take a look. It's an interesting section to learn about how to prove something like this, but the proof is really just a lot of algebra. And so, first of all, if we take any old circle with center AB, and we'll call the radius r, you remember the equation for this circle is x minus a squared plus y minus b squared equals r squared. Okay? And if we look at any point, you remember the power of a point. Let's call a point, I've already used a and b and x and y, so why don't I call power of a point mn equals the distance to the center of the circle squared minus r squared. Well, if a point is over here, mn, that distance is just equal to m minus a squared plus the distance squared, sorry, is equal to m minus a squared plus n minus b squared, and then we have to subtract r squared. So for a general circle and a random point in the plane, here is the equation for the power of that point. And actually, let me just double check that that's in this shot. I may not have set this up right. Oh, good, it is. Okay, so what can we say about two circles? And this might be the only interesting, right in the beginning, the only interesting geometric fact. So I take two random circles. Circle here with center AB, and a circle over here. Remember, they're non-concentric. Didn't quite get the center right. Circle here with center CD. And one thing we can do is just change our coordinate system so that these both lie on the x-axis, so that we get rid of the y coordinate of the circle. So that's just a symmetry argument. In other words, if the line connecting, not doing a good job of drawing tonight, if the line connecting the circles, the center of the circles is that, and then a perpendicular looks like that, if we just rotate this and just pretend that that line connecting the center of the circles is the x-axis, and this perpendicular is the y-axis, none of the geometry changes. So to make our lives easier, and this is just a nice little easy to see geometric fact, and it's going to make our lives a lot easier doing the calculations. So let me just draw it a little better. So here's a circle on the x-axis, here's another circle on a different part of the x-axis. And we're going to call this circle A having center A 0, and we're going to call this a circle having center, let's just call it B 0. And this circle we'll say has radius little r, and this circle has radius big R. Okay, so this is the picture of the circles we're going to look at. This is the first time where I'm a little bit out of room. Why don't I erase the title? Let's see if I can just do the calculations up here. Okay, so the power of a point with respect to this circle, power of a general point x, y, is going to be x minus a squared plus y squared minus r squared. That was the definition of the power of a point. And we want to find out when is this equal to this one, which is equal to x minus b squared plus y squared, oops, not equals, minus big R squared. Minus big R squared. Well, It's not too hard. It's not too hard to go through this calculation. You see the y squareds cancel out on each side, which is nice. And this says x squared minus 2ax plus a squared minus r squared equals x squared minus 2bx plus b squared minus big R squared. Well, now the x squareds cancel out. And I move 2bx to this side of the equation, and I move a squared minus r squared to this side of the equation. And I get, let's see, I get 2b minus 2ax equals b squared minus a squared plus little r squared minus big R squared. And you can see, and unfortunately I'm going to be out of room here. Let me skip down here. This is going to mean x equals b squared minus a squared plus r squared minus big R squared all over 2 times b minus a. Okay, so that's my equation. Now remember, all of these are constants. A is a constant; it's just the center of the circle. B is a constant; it's just where the x coordinate of the center of the circle. R squared is the radius. Big R squared is the radius. So this is a constant. So this says when x equals this constant, the powers of these two circles are the same. And let's just say that's here on the x-axis, and that's just a vertical line parallel to the y-axis. And notice, because it's a line parallel to the y-axis, by definition it's perpendicular to the x-axis, which we said is the line connecting the center of those two circles. So this whole section, the proof of this theorem, is nothing but algebra, but it's an interesting geometric fact that the locus of points whose powers with respect to two different circles, two non-concentric circles, are the same is a line perpendicular to the line connecting the centers. This line is called the radical axis of the two circles. And you'll see why we needed the constraint that they weren't concentric, because if they are concentric, it means they have the same center, and we would have x minus a squared and x minus a squared here, and everything would cancel out, and you would not have any points that had the same power. So it's just a nice little theorem. Learning a little bit more about the power of the circle. There's a great exercise in this section asking you to give a geometric construction instead of an algebraic proof, and that takes a little bit of thinking on how to do that, particularly in the situation where the circles are, one circle's inside of the other circle. So giving a geometric construction to find this line when you have a circle here and a circle here, like that, that's actually an interesting exercise. But all in all, this section is really just a lot of algebra, and hopefully it's going to get you a little bit more familiar with the power of a point, and you've learned a new geometric object called the radical axis of two circles. Okay, section 2.3 is tomorrow. Thanks for watching.